All right, our next topic is population growth. We are dealing with both population exponential model as well as logistic. So just a brief thing, relative growth rate means the growth rate of, say, a population relative to the population. So if we write that in an equation, we have growth rate, the derivative, so the derivative of the population with respect to time, compared to the population is some constant k, where k is the relative growth rate. And this should look familiar because this is the basic equation we've been dealing with. dp dt equals kp. It's the same thing that we have, and we have our solution of p equals c e to the kt. Another way to write this is if we have p sub 0, or in other words p of 0, then that's what our constant c will be, since e to the k times 0 will be 1. So this could also be written as p equals p sub 0 e to the kt. Let's take a look at an example. We have relative growth rate of a city is 0.9%. The current population is 50,000. Write a differential equation. So we'll look at a dp dt relative to p equals 0.009, since that's a percent, or dp dt equals 0.009 p. Now we're going to find the equation. We can go straight to p equals p sub 0 e to the kt, or in other words, p equals 50,000 e to the 0.009 t. Now, I'm not going to re-derive that equation we've done multiple times. It is just something you have to know. Now it says, for the third part, superimpose p of t on a slope field. I've set my calculator up. So it's already ready. I set a lattice of 15 for x, 10 of y. So let me go ahead and draw it. And I've also put in the equation, the 50,000 e to the 0.009 t, and I can say draw that, and we have our graph that's superimposed on top of our slope field. Using the calculator is much nicer than doing all that stuff by hand. All right. Now to the meat of it all right now is the logistic equation. We've looked a little bit at the logistic equation, but it's mainly on seeing the graph. We haven't been taking the equation, the differential equation, and solving it. We have dp dx, you could also say dp dt, whatever your variable is. Typically it's going to be t. Relative to p equals k times 1 minus p over m. This one, we could also write it as dp, and I'll just write it as t, equals kp times 1 minus p over m. So typically you can have it in this form or this second form, where m, as you know, is the carrying capacity, k is some constant, and a is found using the initial condition, often p sub 0 or time 0. We've done several graphs like this. Let's take a look at what this is telling us. If we write our equation, and I would want you to write it multiple times, because for right now, I'm not going to derive this. I'm going to save that for a later chapter. It requires us to know partial fractions, and I don't want to spend time with that. We're just going to use it for right now. When p equals m, we have a horizontal asymptote. And you can see that here. And what is that known? That's our carrying capacity. This is where our derivative for this y value, this p value, equals 0. And we have another one here at the p equals 0. We will have our derivative equals 0. So in both of those spots. What if P is greater than M? When we're looking at him, so P is positive. If it's greater than M, then our derivative, dp dt, is less than 0. So P is decreasing. And you can see that here in this red one. What if P is less than M? Then dp dt is greater than 0. So P is increasing. And we're looking at that situation here. And I'm assuming that P is positive here. We could also look is where is there an inflection point? We can solve it. We have done that already. But when you're looking at that inflection point is when our curve is going to be changing from concave up to concave down, and that value is going to be 1/2 the difference of these 0 and M. And it's, you could say 1/2 the sum of them, but since it's 0, it's not going to really matter. So it's halfway between those two horizontal asymptotes is where we're going to have it, so it'll end up being 1/2 of our carrying capacity, and in this case, we're going to have it at 50, right? That's going to be where we're changing from concave up to concave down. That's not something you have to memorize, but it is something that's just good to be aware of. Let's start to use these. We're going to find a logistic model for this situation. Again, write it. It'll help you to remember this thing. We have P, M minus P. The solution is M1 over the quantity of A plus E to the negative KT. So we're just going to plug it in. P equals, the carrying capacity is 200. We have 1 plus AE, the constant's negative 0.02. Now we're going to use our initial value in order to find out what A is. So we'll say 50 equals 200 over 1 plus A times 1, because that value will be 1 e to the 0. So we can multiply both sides by 1 plus A and divide by 50, and we'll get 1 plus A equals 4, so A equals 3. And that gives us our equation, 200 over 1 plus 3 e to the negative 0.00 or 02 t. All right, let's go to the next page. Basically, we're just going to manipulate this stuff so we can have a better feel in what's going on. And then again, we will derive it later. So we have a little different form here. Let's rearrange that. So to dp dt equals P over 40 times 3 minus P over 200. Now that's not the exact form. We want to get this out. So we'll write it as P over 40. Let me pull out the 200. So 1 over 200 times, we're going to multiply 200 times 3. We have 600 minus P, or in other words, 1 over 8,000 times P, and then 600 minus P. I'm putting this so we can see the stuff better. Right now we can see that M equals 600. Our carrying capacity for this situation is 600. There's multiple ways to go about getting this next one. We could say that K over M, or in other words, K over 600 equals this fraction here, 1 over 8,000. Solving for that, we have 600 over 8,000, and that gives us 3 over 40, which is the same thing as 0.075. And that's all we are asked to do here. We're going to find K and M. Another way you could do is if you want to put it into that form K over M, right now we have 8,000 on the bottom. We could multiply by 600 over 8,000 to the numerator and the denominator to give us 600 on the bottom, and that will give us our K value on the top, and that's going to be equivalent to that fraction, what we just did. Let's look at the next one. So it's similar to that second form. We can factor out the 0., you can even zoom in a little bit more, 0.03p, and then we have 1 minus. Be careful, there's a lot. You can count them up here, and you get 0.002p. Let's rewrite that. We have 0.03p times the quantity of 1 minus 1 over 500p. And let me factor out that 500. 0.03p over 500 times the quantity of 500 minus p. So at this point we can see everything. We have K equals 0.03, M equals 500. Let's write the equation what we would have right now. It would be P equals 500 divided by the quantity of 1 plus A e to the negative 0.03t. And at this point we don't know A. We would need some point, that initial value, in order to figure that out. Alright, on to the next one. Identify K, the carrying capacity, P sub 0, the initial value for the following logistic equation. By looking at it, you can see that our carrying capacity is going to be 650. We already have the basic setup. Let me rewrite it just a little bit, and we'll say e to the 3.5 times e to the negative 0.5t. Let me write my fraction correctly. Now we can see that our K value will be 0.5. And in order to find out what our P naught is, P sub 0, that's our value when our time is 0. So just plug it in. We have 650 over 1 plus e to the 3.5 times 1, but that just gives us that. And that's it. Let's have a little bit of a situation here where we can have a context. The number of students infected by the flu at MV is P of T equals 400 over 1 plus e to the 1.946 minus 0.05t, where t is the number of days after the problem was realized. The flu is just beginning right now. There's a lot of people that are getting sick. Show that P of T is a solution to the differential equation. Find K and M. As far as this, where we're at, the only thing I want you to do is realize this is of the correct form. It's the correct form of P equals M1 plus A to the negative KT. So it's the solution to dp dt equals K over M P times the quantity of M minus P. That's all. And then estimate the P sub 0. So we're going to have, just plug in 0 into our equation. We're going to have 400 over 1 plus e to the 1.946, and when you take out your calculator and do that calculation, you get 49.996. So then we would give this answer clearly when the problem was realized. "50 students were infected with the flu." And that's it for our logistic equations. It is something you're familiar with. It's something we'll derive it later on. But for right now, we'll just use it and be able to understand what our derivative is telling us when we are using this. And that is all.